Glorious Gadgets is a retailer of astronomy equipment. They purchase equipment from a supplier and then sell it to customers in their store. The function C of x given here models their total inventory cost in dollars as a function of x, the lot size for each of their orders from the supplier. The inventory includes such things as purchasing, processing, shipping, and storing the equipment. We have two questions to answer. One, what lot size should Glorious Gadgets order to minimize their total inventory cost? This answer must be a whole number. And two, what is their minimum total inventory cost? So we need to minimize this cost function, so we'll apply the first derivative test, which means the first step is to find the derivative, set it equal to 0, and find their critical numbers, which is where the min or max values will occur. So if this is c of x, notice that c prime of x would be equal to the derivative of 3.5x, that's 3.5, plus the derivative of 9,000 x to the negative 1. So we'd multiply by negative 1, that'd be minus 9,000 x raised to the power of negative 1 minus 1, that's negative 2. And the derivative of a constant is 0. So now we'll set this equal to 0 and solve for x. Let's go ahead and add 9,000 x to the power of negative 2 to both sides. So we'd have 9,000 x to the power of negative 2 equals 3.5. Let's write both of these in fraction form. So we'd have 9,000 over x squared equals 3.5 over 1. And now that we have a proportion, we can cross multiply and solve for x. 3.5 times x squared must equal 9,000 times 1. So 3.5 x squared equals 9,000. Now we'll isolate x squared by dividing both sides by 3.5. Simplifying, we have x squared is equal to 9,000 divided by 3.5. And now we'll take the square root of both sides of the equation to solve for x. Now algebraically, we are going to have a positive and negative solution here, but because we know x cannot be negative, we'll only find the positive solution, or the principal square root. So now we'll go to the calculator. So we have x equals the square root of 9,000 divided by 3.5. Again, our answer must be a whole number, so we'll say our critical number is approximately x equals 51. So we have one critical number, which is x is approximately 51. Now we can't assume this is the x value that's going to minimize the inventory. We do need to apply the first derivative test. So to do this, let's sketch a number line. Our critical number is approximately 51. So we'll use the first derivative test, which means we'll test the sign of the first derivative to the left and right of 51 to see if the function is increasing or decreasing. From this information, we can determine whether we have a min or max value at x equals 51. So for our test values, let's say x equals 40 and x equals, let's say 60. Any values to the right and left of 51 would work. And again, we'll sub these test values into our first derivative, which we found here. So going back to the calculator, c prime of 40 would be 3.5 minus 9,000 times 40 raised to the power of negative 2. Notice how the first derivative is negative, which means the function is decreasing on this interval. So in this interval, the first derivative was negative or less than 0, which means the function is decreasing on this interval. And now we'll test the sign of the first derivative at x equals 60. So because we already have this expression in here, we can just press second enter and change the 40 to a 60. And notice how at x equals 60, the first derivative is positive. So the first derivative is positive over this interval, which means the function is increasing over this interval. And this is good news because that means that x equals 51 or approximately 51, the function changes from decreasing to increasing. and therefore we are going to have a minimum function value at x equals 51. So to answer the question, a lot size of 51 will minimize the total inventory cost. Now for the second question, what is the minimum total inventory cost? We want to evaluate the cost function, not the derivative function, at x equals 51. Let's do this on the next slide. So the minimum total inventory cost is going to be C of 51, which is going to be equal to 3.5 times 51 plus 9,000 times 51 raised to the negative 1 plus 6,000. And now we'll go back to the calculator. So we have 3.5 times 51 plus 9,000 times 51 raised to the power of negative 1, right arrow, plus 6,000. Because these are dollars, we'll round to the nearest cent, so we'll say it's approximately $6,354.97. So the minimum total inventory cost is $6,354.97. Notice how we use the whole number solution to the first question to answer the second question. Before we go, let's go ahead and verify this result graphically, and we'll do this by analyzing the graph of c of x. So our cost function c of x is graphed here, and we found using the first derivative test that we had a minimum function value at x equals 51, which is approximately here at this low point. And we can tell from the graph that the total cost of the inventory when x equals 51 is around $6,300. Notice how we can also verify that the function is decreasing to the left of 51 and increasing to the right of 51. Even though it's not increasing very fast to the right of 51, it is going uphill, moving toward the right. I hope you found this helpful.